Здравствуйте, меня слышно? Максим, ты меня слышишь? Отлично, спасибо.
А это уже есть.
Да. Я сейчас, может быть, батарейки попробую поместить. В принципе, можно яркость немножко уменьшить, если...
Да, для картинки-то сзади не обязательно, а остальные контрастные сзади были.
Не, у нее инфракрасный порт, мне кажется...
Батарейка. Тут надо просто включить, да?
Нет, ты скажи, не надо направлять на компьютер.
А, не надо?
Да.
Не знаю, где они направляют.
Ну вот, все нормально.
Вот сейчас я буду.
Вот это аккуратненько.
Ага.
Как видно.
Сейчас по слайду. 80.
А где ты видишь, что сколько их?
Справа вверху, да?
Ну, сверху-то да, ну, я меня еще перегружена. Попробуем на слайд. Я просто не знала, сколько подгружено, я решила чуть-чуть поиграть.
Объясни, как эти смешанные цвета.
Ну, смотри, мы взяли это нашу метрику.
Нет, смотри, обычно у тебя есть отдельный кадр, а отдельный стоят.
Ну, подожди,
Да, потому что у тебя там мало людей, и это разное сложно.
ну, я в таком виде не хочу, что это.
Все нормально? Так, пойду я позову. Сейчас я позову сейчас нашу.
Да вроде я сказал всем, но...
А мы начали через себя?
Ну, через 2-3, да. Что такое?
Видимо, нет.
Я не успел уже микрофон включить, попробовать.
Что ты хочешь попробовать?
Микрофон просто включить.
Ну, хочешь попробуем?
Понятно, как звук будет.
Ну, может быть...
А те, которые не видят?
Так, сейчас.
Не, лучше потом. Лучше потом. После семинара.
Ну, давай потом.
Я тогда принесу, попробуем.
Ну да.
Вот так будет лучше. Юля, у тебя везде фон белый, да, такой?
Везде, да.
Ну, отлично. Ну, нет, нормально. Я как раз уменьшил яркость, чтобы было видно.
Хорошо, спасибо.
Сейчас я...
Да. Не голосуйте, нужно смотреть, чтобы все равно было, дальше так, с самого начала. Уже можете начинать, извините. Все конкурсы разные стоят. Ну ты спрашиваешь про смешанные. Ты спрашиваешь про смешанные.
Нет, ну, пожалуйста, они отвечают по импульсам.
принципе, вот чем запрещена принципиальная комбинация HG, HG, да?
Какая это определенная?
Да.
Так, ну что, вроде всех, кто есть, позвал. Давайте начинать наш семинар. У нас сегодня выступает Юлия Агеева, МГУ и ИЯИ, и доклад на тему космологической модели скалярно-тензорной теории Хорндески. Это доклад по материалам кандидатской диссертации. Я так понимаю, это формально еще некоторые мероприятия для МГУ, да? Некое выпускное мероприятие.
Там надо тоже
А где вы, извините, где вы защищать планируете?
здесь влияет.
Правильно?
Это вот на основе каких работ? Physical Review, правильно?
Да. Это Modern Physics Letters, это успехи, а это тезис Кларка 18 года.
Правильно понимаю, что организация будет МГУ, да? Организация, в которой подготовлена диссертация.
А вот у меня был такой вопрос, когда автореферат пишет, что там надо написать эту вещь. Я хотела спросить.
Даже не когда автореферат, а когда вы будете подавать. Нужно определиться, какая организация, где вы выполняли диссертацию. Это будет зависеть от того, какая организация напишет вам заключение. Будет ли это МГУ или наша организация.
Это хороший вопрос, я не знаю.
Юлия формально МГУ, да.
Ну, тогда
Еще идет. Да, еще.
Буквально сейчас она заканчивается.
В конце сентября заканчивается.
Что?
В конце сентября аспирантура заканчивается.
Понятно. Нет, я просто хочу сказать, что тогда по этой логике она же в МГУ делает работу.
В МГУ и у нас, потому что она у нас тоже чисто.
А мы можем и тут работу выполнена там-то и там-то.
Организация должна быть одна. Формально. Не бывает такого, что две организации...
Нет, понимаете, мы, конечно, мне, пожалуйста, нам даже лучше, что у нас столько работы хороших, но МГУ уже они могут обидеться.
Я понимаю,
вопрос скажет, но мы там платили деньги, трали, там, а вы взяли...
Как вы с Сергеем договаривались, мы же заведующий кафедрой?
Мы про эту тему не разговаривали.
Вам нужно обсудить, поскольку это, кажется, такой ерундовый вопрос, но на самом деле он...
Да, он уже вставал.
Коллеги, добрый день.
Они могут, а для них же тоже это, они теряют одно очко, скажем так.
Ладно.
Вот этот вопрос...
Да, мы, наверное, ничего не приобретем от того, что если вы скажете, что выполнил диссертацию у нас, наверное, ничего не получится. Для совета все равно, потому что защиту представителей.
А кто-то удаленно что-то хотел сказать?
Да, я хотел сказать. Меня не слышно?
Сейчас. Так, а почему-то так тихо-то? Да. Сереж, почему-то тебя слышно.
А так?
Сейчас я погромче сделаю. А можешь еще раз сказать?
Алло.
Да, вот теперь слышно.
Ага, спасибо. Я хотел сказать, что научный руководитель у Юли Сергей Миронов. Сергей Миронов не имеет никакого отношения к нашей кафедре формального. Поэтому это либо ИТМФ, либо ИЯИ.
В том смысле, что он не может выступать как научный руководитель? Ты в этом смысле?
Нет, он может выступать, но мы не можем, как кафедра, давать, наверное, заключение о том, что на кафедре выполнена эта работа, потому что руководитель не работает на кафедре. Я совершенно правильно считать, что Юля выполнила работу в ИЯИ, в теоротделе, сначала под руководством Рубакова, потом под руководством Сергея Миронова, и все. И с университетом не связываться, там эту бумагу должен будет проректор подписывать, это месяц займет.
Это лучше, единственное, но, Сергей, если вы меня слышите, в этом случае у нас не будет проблем.
Николай Валерьевич, не должно быть, не должно.
Все, ваше слово закон.
Кандидатский как? Специальность?
У меня сдавали 1, 3, 3 и старая, я не помню год. Теоретическая физика.
А старые зачитались?
Да.
Английский и философия поставили.
И специальность. Да.
Считается, да?
Да, я заходила в отдел аспирантуры, потому что там говорят, что из-за того, что поменялось только циферки, а название не поменялось, то все нормально.
Хорошо, даже для нас так нужно. Еще одну диссертацию.
Хуже будет списка от номера, да?
Их можно Ладно, давайте начинать.
Okay, I guess I switch to English. Yes. Today I would like to tell you some aspects of cosmological models in Horndeski theories, or frankly say in subclass of Horndeski theory. The content of my talk is as follows. I start with a brief motivation, then I recall our very beginning work on strong coupling problem using dimensional analysis in Horndeski genesis. After that, I turn to construction of stable, free of strong coupling problem, non-single cosmological models. This is not only genesis or bounce itself, but genesis and bounce will be suited with inflation or kination stages. After that, we go to the problem of strong coupling dimensional analysis, because it's not so good, and actually one should use analysis of amplitudes, diagrams, and find strong coupling energy scale using diagrams, but not naive dimensional analysis actually. And finally, I briefly discuss interesting thing for cosmological context, entirety relation and entirety bounds, which we would like to use again to find strong coupling energy scale, for example in bounds or in genesis, because dimensional analysis is not so good sometimes. Okay, today big interest due to alternative or completion scenarios to inflation. It's not just academic interest, but if we close some bounds or genesis or other models of early universe, we somehow indirectly confirm inflation paradigm. And also it's always interesting to have something alternative, as well as if we have some completion to inflation, we can cure it from initial singularity. Okay, we will construct genesis. In further slides, I show you some plots about it and bounce model. And what we want to avoid, we would like to use Horndeski theory in order to help evaluate null energy condition, in order to build something non-singular. Next, we would like to obtain stable whole evolution, I mean bounds of genesis plus inflation plus spination, and so on, and no instabilities during this whole evolution. It means that we should avoid no-go theorems in Horndeski. And finally, of course, we would like to avoid a strong coupling problem in the very beginning, in the past of our universe. We choose some specific parameters to cure this problem. Okay, universe with bounds, what is it? The evolution of the universe begins from contraction. Hubble parameter has minus sign, and then bounds occurs. Hubble parameter changes its sign, and then, for example, inflation information can begin. And for genesis, we have another beginning of the universe. We start from flat Minkowski space-time, empty universe. Scale factor in metric equals to some constant, usually.
Excuse me. You have inflation after the genesis.
Yes, we can have this.
So then, does this mean that you don't have any experimental predictions whatsoever?
Yes, actually, we have only. Now we have experimental prediction for spectrum, right? And actually,
yeah, but this is
yes. Not only inflation, we have some number for NS, I mean, and for R ratio. And we can compare it for some models, for example, for bounds with these numbers. Why not?
So this is because you have some specific
yes, some specific mechanism for generate perturbations in bounds, for example, without inflation.
So if you don't have inflation, then you do have
but we can see genesis with standard inflation, and then everything will be okay with
but no predictions.
Yes, but actually I guess that we can choose some parameters to compare our model or to skew it with experimental data. I just want to realize what are the experimental predictions which are different from inflation, from the standard inflation. In the case if you have inflation after the genesis. In this sense, I guess there is no prediction.
So this is some specific type of inflation which follows the genesis.
Yes.
And you solve basically the problem of initial singularity in this case.
Yes. Using genesis.
And if you don't have inflation, then you have a spectrum of predictions, right?
Yes, without inflation. Yes. Pavel Petrov will talk about this because this paper about bounds and spectrum goes to his PhD thesis. Yes, after genesis, we can go directly to reheating combination or to inflation, for example. Briefly recall what is null energy condition or null convergence condition. Then we talk about modified gravity. This inequality called null energy condition after Hawking, Ellis, and Tigger, if I'm not mistaken. So firstly, let us consider some simple case. Then Friedman-Leveter-Walker universe has homogeneous and isotropic matter in it, usual components of energy momentum tensor, and after some algebra, we combine two Friedman equations and covariant law of energy momentum conservation. We arrive to these two equations, and we also omit curvature term contribution. If we think that null energy condition is satisfied, then we obtain this inequality, and immediately we see that if this multiplier and this multiplier, greater than 0, we see that in past somewhere we have arbitrarily large energy density and Hubble parameter. And this is what we call singularity during this talk. And we would like to avoid this situation. That is why we built Bowers and Genesis. But violate this condition and obtain opposite sign here, it's not so easy for any known matter. For example, for usual scalar field, it just automatically satisfied. That is why we turn to scalar-tensor theories, to generalized Galileans, or to Horndeski theory. It was opened by Gregory Horndeski in 60s, but 70s, and reopened in 2010s. Full Horndeski Lagrangian shown, and it is as follows. Here we have several number of arbitrary functions of scalar field phi and its kinetic term x, like that. And actually, for our purposes, it is enough to use this Lagrangian.
May I ask you a very naive question? So this theory predicts the existence in spectrum massless scalar field, yes?
Yes.
As a physical field. It's not auxiliary field. It's
during Bowers and during Genesis, it's auxiliary field, but
no, in spectrum, we know it's simple. It describes massless particle. Yes?
Yeah.
And this particle interacts only with gravity. Yes.
Right.
It can be massive.
We consider massless, I guess now. Yes, but okay, maybe it can be massive.
If G2 has pi squared term,
Yes.
it can be massive.
G2, this term, something like potential.
So in principle, it could be massive, but nevertheless, it's stable. Yes.
We try to build something
That
stable.
depends on the function, but it can be made stable.
It depends on integrators. Decays integrators. Massless particles do not decay. Well, for massless, yes, but for massive.
No, I mean it's stable linearly. Direction. Yes.
Okay. Actually, for some modified Genesis model, we also add here the dependence on x in G4 and this term also, but mostly we use this Lagrangian. To talk about instabilities and about perturbations in our theory, we turn to more convenient for our purposes ADM metric in this form. Here we have some function of time before differential squared of time. This is cosmic time will be, and this part connected with three-dimensional metric and its perturbations. N called lapse function, I and G called shift vectors. Fortunately, alpha and beta in these parameterizations are not physical, and on quadratic and cubic level, we can write down something unconstrained, something free from these alpha and beta perturbations, because we have constraints on them, and they work on second and cubic order. And again, some advertisement of Pavel Petrov talk. Actually, we take very simple functions here, actually in ADM Lagrangian, and using this simple function, we can even analyze higher order perturbation series of action and unconstrained higher order equations, obtain them without alpha and beta, and actually without alpha and eta and some other perturbation. Okay, for this talk, I will talk only about quadratic action and cubic one. That's enough for now. I should say that we work in unitary gauge, okay, and here we have second order action for tensor perturbation and scalar perturbation. Okay. Briefly talk about no-ball theory. The main statement is that at some moment of time, then we talk not only about genesis or bounce itself, but about whole evolution. Somewhere at some moment of time, we can meet instabilities, and of course we don't want to have such situation. That is why we try to somehow avoid no-ball statement argument. And this is the condition of how to avoid it. Since we would like to have non-singular scale factor, we should work with to this function, and the only way that we work in the framework of Horndeski is to obtain such asymptotics of these coefficients that they goes to zero, then time goes to minus infinity. I will talk only about past of the universe. Another solution of this problem is to remove Horndeski and go to beyond Horndeski or closed theories. There is no such problem in these models. But anyway, we stay in subclass of Horndeski and try to build a model with such asymptotics in order to avoid no-go argument. However, we meet another problem now. Let me briefly show that in our simple model, we have that this coefficient equals or proportional to coefficient in Lagrangian near which scalar. It means that we have now effective Planck mass goes to zero. What this means? This means strong gravity or strong coupling with gravity, because Newtonian constant runs to infinity, and that is why naively we have strong coupling in this model, but we should elaborate with this problem and try to find good parameters of Lagrangian to avoid it, and we can do it actually.
Excuse me, I didn't understand about the perturbations of the previous.
Okay.
So do you have 2 degrees of freedom, one tensor and one scalar, right?
Yes.
So this is a scalar, and right now it is massless, and it is present from the very beginning to the very end.
Yes.
And this is a physical degree of freedom.
HG and zeta physical degrees of freedom.
Okay.
Yes.
So you can use this scalar just to, I don't know, for that matter. No.
Yes. Why not?
Okay.
Yes. The only physical degrees of freedom only these two guys. Yes.
And another question: if you have inflation, do you have either curvature perturbations due to massless scalar, or at this point you want to make it massive? Because any massless stuff produces either curvature perturbations due to inflation.
Oh, actually, I don't think about this. Maybe we should discuss it later. Now I cannot answer this question.
Yeah, but
maybe
producing mass will help.
We can curate this. Okay. Now, let me turn from covariant formalism to our favorite ADM formalism, because for this task, it's easier to work with it, to build genesis and bounds using ADM formalism. Actually, we don't want to find G2, G3, and G4. They have more complicated form, but we choose some convenient A2, A3, etc. functions. Okay. Here in ADM, this is nothing but Hamiltonian reformulation of GR. we have another variables, time and lapse function. Here, this guy is three-dimensional metric. In action, we also have this combination, and K is called extrinsic metric, also three-dimensional. To this end, to build genesis without strong coupling, we choose quite simple Lagrangian functions, which admit genesis solution in the past, avoid no-go argument, and avoid strong coupling. Let me show how we realize this scenario. Now I will talk only about asymptotic behavior at this time, when time runs to minus infinity. For this time, we choose this behavior of f function, see some constant, and we also choose small a as follows.
Excuse me. You are making your coefficients in the Lagrangian as functions of lapse, and is this a general covariant?
Yes, also.
Why is that general covariant? Yeah, so n is not a invariant, right? Lapse function.
In our simple setup it equals unity, but
Okay.
yes, in more general case, I should think. Then it equals unity, I think, everything.
So just general question about general covariance. So you want general covariant action, right?
Yes.
And in this, okay.
It's not easy to see this on language of ADM, I think, yes, but maybe we can try. Okay, maybe later. So we can write down equations of motion in this theory, find out that it's possible to obtain genesis behavior in the framework of this ansatz. Means that in minus infinity we have scale factor equals to some constant, to unity, and loss function also equals to unity. It means that we have flat Minkowski space-time in minus infinity at minus infinity times, and this is nothing but genesis. Also, in this ansatz, we have desired behavior of these two coefficients and also in scalar sector as well. In minus infinity, it means that we avoid no-go argument. And we immediately obtain some constraint on parameters of Lagrangian for now. As well, I should say that in order to build genesis in this form, we also have one more constraint on delta parameter of Lagrangian. We have them here. Next, how we analyze strong coupling using naive dimensional analysis. We have two characteristic energy scales, classical one and strong energy scale of strong coupling. We should compare them, and this is the only condition then classical analysis is legitimate, of background solution is legitimate or consistent. For classical energy scales, it's quite simple to find them. They're associated with a Hubble parameter, its derivative, or with scalar field. But the strongest conditions we have with this classical energy scale. And now we can turn to calculation of strong coupling energy scale. Start with the scalar sector of perturbations. Here we have a lot of terms, but fortunately in our simple setup, we have quite simple behavior, quite simple asymptotics for them. They have the following form, where x is just also simple combinations of Lagrangian parameters. After analysis of all terms, we can write down our Lagrangian schematically like that and proceed dimensional analysis of all terms. Indeed, in this Lagrangian, we have some coefficients, cubic order, we consider for now cubic order in scalar sector, some number of time derivatives and some number of special derivatives. In this form, it's easy to analyze in dimensions. And one more step is to turn, of course, to a canonically normalized field for scalars and for tensors. We also will do it. After some algebra, we arrive to these schematically written terms in Lagrangian and find out that energy associated with these coefficients has a very simple form, actually, just some power law behavior. After that, we compare this classical energy scale and this strong coupling energy scale and find out condition when there is no strong coupling problem in scalar sector for now. Again, recall that A and B is the number of time and special derivatives in our for each term in Lagrangian, cubic Lagrangian for scalars. I can say that the most dangerous, the strongest condition is as follows. It comes from several terms from this Lagrangian, not from all of them. Some provide weaker conditions. The same analysis, I guess I should skip it because it's totally the same for mixed sector. Then we have one scalar, for example, and two tensors again obtain some condition. And the same for another mixed sector, again obtain one another condition. And also we have small tensor sector, then talk about cubic order. It also provides something really simple. To sum up, we obtain some set of conditions on our parameters of Lagrangian, and we can build some plot where all these conditions are shown. For example, under this blue line we have a condition when there is no go argument, we avoid it. And under green line, under red, and I guess orange, we also avoid strong coupling. So this is the region where everything is okay with our genesis and framework of Horndeski. As I said earlier, we analyze only cubic action, but of course one can write down fourth and so on, and find out from these interactions of higher order another strong coupling scales, and maybe they can break everything, but functionally no for our simple model. And this is.
Can I ask about the previous slides here? So above everything is good, above the blue line and below others.
Yes. In black framed triangle, everything is good.
So scalar is worst of them all.
Yes.
And what is the blue line?
Blue line correspond to no-go argument to this.
To no-go.
Yes.
So scalar problem with strong coupling is the worst.
Yes. And
okay.
we check other models and other steps. Scalars always the strongest condition, or provide always the strongest. Okay, another advertisement of Pasha talk in future about higher order analysis of strong coupling problem using dimensional analysis. Now we can turn to another huge chapter of my talk. Of course, it is connected with the previous one because earlier I showed you in details how we analyze strong coupling, and now I just omit this totally the same considerations and talk only about the steps of how we build bounds, then sew it with inflation, of bounce, of genesis, assume with octination directly, and so on. So what we will build here? We consider bounce in the universe, two types, then universe go to inflation, and then to reheating of octination. And then bounce in the universe go directly to octination stage without inflation. As well as we consider some interesting combination of genesis model with the bounce, and then universe go to also to inflation or to octination. And finally, some simple model of genesis, which also can go to inflation or lives without inflation and go to octination. Okay, let's start. Again, we work in ADM formalism, choose some good ansatz for our Lagrangian function. Again, we will choose parameters in such a way that avoid a lot of problems we meet with, instability, strong coupling, and so on. Now we consider more general form of these two functions, because earlier, when we built only genesis, we consider unity here.
Excuse me, I realized that these coefficients are functions of x, and x is dignified squared.
Yes.
So that's why you have n here.
Yes, x proportional to n power minus 2.
Okay.
Let's talk about, again, in details, I talk only about bounce followed by inflation, because all other models actually can be built in the same manner. So in details, we consider only this model, and there are stages we would like to have. We would like them to be stable and so on. Okay, the universe starts from contraction. We have we want to obtain power law behavior of scale factor, then bounce occurs. After that, after a short period of time, we go to inflation, and we would like to obtain, of course, a couple parameter as a constant. And finally, go to octination epoch. It means that we would like to transfer Horndeski not so clear field to a master scalar field and restore general relativity on this stage. So it's quite natural to obtain something like that on later stages. Okay, start with contraction. During contraction, we would like to have such solution here, and in order to obtain it, we will choose healthy parameters in Lagrangian functions at minus infinity. At these times, we can again write down equations of motion. They provide us two roots. We take only one because only this root for V0, it's a parameter of Lagrangian game, and chi is a parameter of Hubble. Only this root corresponds to stable solution. Also, we have another constraint here. We would like to have expression under square root bigger than 0 for sure, and actually this provides another set of constraints on parameters. Another set of conditions comes from stability argument. I write down simple coefficient, and GS has a more complicated form as well as some speed. Again, these expressions provide us with some conditions on parameters. Next, again, we can talk about Noble theorem and obtain, after some algebra, this condition. Finally, yet another constraint we obtain, then talk about our favorite strong coupling problem. Totally the same analysis, and at the first, which I talk about at the first part of my talk, we arrive to this condition, and together with the previous one, we obtain even more simple condition on chi. one can note that if we recall the behavior of a scalar factor, we see that contraction velocity increases with time. And the final argument connected with Belinsky-Palatnikov-Lifshitz phenomenon. For example, if we consider for tensor modes the following equation of motion, here we omit gradient term, we find out that there is two solutions. One is a constant as usual, and one have power law behavior. So if we want that it decays as time increases towards zero, because time runs from -infinity to zero, we should we must have the following condition, one more. But fortunately, it's weaker than previous conditions, so just forget about it. So to sum up, we arrive to this simple set on parameters of Lagrangian, and to this end, we can determine the space of parameters of Lagrangian x0 and y0, and here again, white triangle is a region of parameters where everything is okay. Everything is stable during contraction. Now we talk only about contraction. No strong coupling, and so on. Actually, in this picture, we can see one another condition coming from subliminality, and here I restore this missed condition. Actually, it somehow squeezed this white triangle. So we set mu to something and c to something, and find out healthy parameters of Lagrangian.
Can you repeat again? There was a discussion last time that when you were making talk that subliminality condition is a condition that the fastest mode should be a tensor mode, right? No?
No, each sector must, in each sector for scalars and for tensors, this perturbation must propagate not faster than, with the speed not faster than the speed of light.
Certainly not light. Light is just an electromagnetic wave. This is one of it.
I mean that this coefficient we would like to have, let me show formula.
Not faster than the tensor mode?
Yes, in this sense, yes. We every time we have that tensor mode propagates with unity.
Okay.
And in this sense, yes.
Not faster than
unity, and not faster than.
With the fastest tensor mode.
You mean that we have not in our model electromagnetism, that's why we cannot talk about.
No. I just mean differently. You can even introduce electromagnetism, but electromagnetism is not a universal field. It's just one of the fields.
Yes, in this sense, not faster than tensor modes. Yes.
Okay.
And not faster than unity in this sense, yes. I talk about contraction stage, and now we can turn to transition to inflation after bounce and to bounce itself, because actually build transition periods and something non-trivial like bounce is the most terrifying problem, because it's really difficult to obtain stability during this transition from stages and during bounce also. Then we talk about inflation itself. We can easily build it. The question is to healthy assume it with bounce and with kination. At inflation, we have the following answers, and having it, we find from equations of motion that indeed we can obtain Hubble as a constant and lapse as another constant. We can require the following inequalities, and for us it's more convenient to consider these values as independent parameters and rewrite everything else through them. For example, at these stages, we again have these parameters in Lagrangian, so we would like to rewrite them through Hubble parameter and loss function, and also through
Excuse me, I lost myself again. So what is the impact on the new model? What drives inflation?
in Horndeski theory.
So, and what field drives inflation? Is it the scalar, which is massless?
I guess this scalar in Lagrangian, this
So it's massless, but what do you have? Non-zero. What creates h squared? So
it's some complicated function here in terms of covariant formalism, but we also can write some dynamics for this scalar field. It will be more complicated, but
is it a non-zero kinetic term or?
I guess yes. If we come back to covariant formalism, take these functions and write everything on covariant language, we obtain something standard kinetic term and plus.
I mean the field phi is not constant, right?
No,
it's not like the slow roll inflation. Phi is almost constant. This is a function of time, no?
I guess that at the beginning of the inflation, it's 100% that is function of time. But then we would like to restore general relativity during inflation and proceed to kination, where we would like to obtain no Horndeski, but just massless scalar field. But during inflation, I guess there is some. This is not just a massless field during inflation. Something more complicated, I guess. But I cannot write down it now because we never turn to covariant formalism.
And kination is inflation, which is driven by kinetic term of
Yes,
phi.
just by massless scalar field, yes. Another expansion, yes.
So phi is roughly speaking proportional to t,
Yes.
and you have h squared constant.
Yeah,
And,
I guess yes.
Your purpose is to obtain this thing.
Yes, somehow assume that inflation, then inflation, yes.
So may I ask a question? In standard picture, inflation starts at the scale, say 10 to the 15 degree, something like this.
Okay.
And in your picture, the inflation depends on some terms with scalar fields. And what the scale of inflation in your model? It's arbitrary or
it's quite arbitrary and it depends on our parameters, actually.
So it could be, say, the scale 1 MeV.
In these terms, I cannot speak, but...
No, but say, not 10 to the 15 as in standard picture, but say 1 GeV, for instance. Is it possible?
I guess, why not?
So
Just
you don't
depend on
have any
parameters.
experimental objections?
In this sense, yes.
So in this case, you can differ in a drastic way from classical, from classical inflation, I would say, from classical models. Because as I know, in classical models, 1 GeV is excluded, 1 GeV scale. Maybe I'm wrong.
Well, these things we should calculate, actually. In these terms.
Other question. For instance, in Starobinsky model, we have standard gravity plus r squared term. So in this, the action, classical action, depends on one-dimensional quantity, the mass, Planck mass, yes? But in your action, you have, I guess, several dimensional quantities. So the Lagrangian depends on not only on Planck scale, but on other dimensional quantities. In A2, A3, something like that.
No. In this setup, we also have, yes, G4 is a modified Planck mass, yes.
No, you have, I guess you have several, on what numbers, arbitrary numbers, depends your model. 1, 2, 10, 100.
Finally, for example, during contraction, we can, I don't know how to say, we have from this picture 4 parameters. For example, we have some defined C and mu, and take some y0 and x0 from this white triangle.
So we have 4 essential parameters.
Yes.
And they dimensional or dimensionless? No, I mean the Lagrangian, if you consider the Lagrangian.
For example, C, for sure, it is dimensional because it multiplies on time, and then we want to restore all dimensions, so it will have some dimension. But C is something, let me find. This function connects with values near Ricci scalar, so it somehow connects with effective Planck mass.
Well, my question is simple. You mentioned that the scale of inflation in your model, in fact, arbitrary. Yes, it means that it has to depend on some parameters. Your model.
It will depend.
What kind of what differs your model from standard? What's the crucial difference?
I guess that what is the crucial?
What's the crucial difference between your model and Stravinsky models?
Actually, if we take some parameters here, I think that Stravinsky model included in Horndeski, so at some parameters we even can see our genesis or bounds with, why not with Stravinsky inflation, I think, at some parameters. But so in this sense, we can use different models of inflation. We just want to obtain Hubble as a constant, and this is the only characteristic of inflation we use in this setup. So sorry, I don't know how to clarify this moment. Okay, sorry. Next. Yeah, I guess we stop here. So in this simple setup, I should note that we restore general relativity already because F now is a constant, and this is nothing but the coefficient near Ricci scalar. After that, okay, I show already the slide. Again, we find from stability and from subliminal propagation of perturbation another set of conditions on our parameters of Lagrangian, and choosing them from this region, we can build a healthy inflation. Okay, here I just mentioned that these two functions do not change its sign. In our setup, it's just a log, I think. And y is not so good, so we should find Lagrangian function which zero bounds to inflation in more complicated way for this function. Okay, the final stage is kination. This is nothing but stage where we describe everything with massless scalar field and general relativity. Choosing field phi in this way, we can find out that with this Lagrangian we obtain the following solution which correspond to kination. That is why we would like to restore this Lagrangian, for example, at the late stage of kination. How will
excuse me, kination is inflation, h should be constant. Why yeah, this is kind of similar to the, I don't know, some power law stage. Why is it analogous of inflation?
Just because it's again some expansion, nothing else, I guess.
Does it lead itself behave as an inflation? Does it generate perturbations in the same way?
High inflation, it's right. I guess yes, it's some kind of work, and there they generate some perturbation. Yes, but
this slow expansion, like t to 1/3, is enough to reproduce everything.
I guess yes, because to my knowledge, I guess yes, because I see this works, and there kind of generates everything we need in high inflation.
And can you wait for like 50 equals?
Later I show the duration of our inflation, and during kination, I don't know, but later I show that during our inflation we use here, we obtain about 46 folds, yes. But this is during inflation, not kination. With kination, we would like to use it just as something known and healthy, because here we have massless field and jar, so everything is okay. So in order to obtain this form of Lagrangian at the later stages, we proceed with this covariant Lagrangian at later stages, where these terms, we would like to dump them somehow. This is why suppress them somehow. This is why we, again, by some trials and errors, should find some dumping factors which kill these terms at kination. Okay, this Lagrangian corresponds to ADM function as follows, or we can rewrite this function which we try to find in this way, using this power of time in v and y, we successfully suppress these terms. Again, our work is to find healthy parameters here. Let me show you some successful numerical example for bounds with inflation and kination. Here, just all parameters we use, a lot of them. Yes, it's not so maybe beautiful, but it works. And in future, not in future, we already done it. We use some similar model to study spectrum. So this model actually, why not? It's viable for physical tasks, for example. Okay, another detail connected with this function in Lagrangians. They are not so easy, and again, there are a lot of trials and errors to find them in such a way that contraction, bounds, etc. will be stable, and so on. So we find this form of this function, and it works. Finally, the same we have for transition between inflation and kination, something like that. Again, set of parameters we choose. Here, these two strange variables control the duration and how smooth our transition between stages occur. Okay, I write down. Okay, this is the example of our x function from Lagrangian, how it behaves between transition from inflation to kination. So we need to assume different values of parameters, so we choose some step function. Not so easy, but it's not pure step function. You see here we need some, I don't know how to say it, this strange behavior, but it helps us to build what we want. Okay, finally, just some picture of our cosmological models. here we have a Hubble parameter in our setup, contraction, then bounce, and initial stages of initial moments of inflation after some short time after bounce. Next picture for Laplace function, we just control that it's just some constant at the minus infinity. And then we control stability for sure. Here you can think that it's negative values, but we always control ourselves and plot square root of these values, so everything is okay. Again, subluminarity is explicit, and tensor modes have simple form, so we show only this function, and tensor modes also have stable behavior. Okay, here we discuss contraction, bounce, and beginning of inflation, and now we turn to last steps of inflation for Hubble, and then we go to kination behavior. And during inflation and kination, we also have stable and subliminal behavior for scalars. Tensors have the same behavior. Okay, final details is just, I would like to say that full function in Lagrangian is just a superposition of each part, which controls transition from vowels to inflation, from inflation to kination, and so on. And here in our model, we have the duration of inflation like that in Planck units, but we can somehow change it. The same for e-foldings, which we collect during inflation. Okay, absolutely, using the same logic, we can build bounds which go directly to kination. Here I provide you only plots, no details, because we proceed in the same manner. So here we have a slightly different behavior from inflation, kination, right after bounce, and again explicit stability for scalars and subliminal behavior. Finally, if one chooses another setup, another Lagrangian function with additional parameter, then we can obtain models with genesis. Again, take this a little bit more complicated setup. We proceed the same steps and obtain interesting model. Here we start from Minkowski flat space-time in the minus infinity. Then the universe starts to contract. After that, bounce occurs, and then we can go to inflation or to kination directly. Again, there is everything is okay. It's some strange moment, but we check it. It's okay, and subliminal behavior is also right, less than unity. Okay, this big part of my talk connected with non-singular cosmological models ends, and I would like to tell you that model of bounds, where we generate nearly flat power spectrum of scalar perturbation, it's indeed possible to do it. Of course, it's not so automatic, and the mechanism of perturbation of spectrum is not so easy as an inflation. It connected with a strong coupling problem in the past in our models. So another advertisement of Pavel Bezos and...
Can I ask, you have a point that you have basically inflation after genesis.
Yes.
If you would have it for, say, 70 volts, then the mechanism of generating a power spectrum would be inflationary, literally.
Yes.
Because inflation...
Yes, you mean that we know nothing about the beginning.
Yeah, because inflation destroys everything that was before and generates its own perturbations. So the difference here is related to 46 volts. No inflation at all.
Here, no inflation at all. Only bounce, and we compare it to its power spectrum with observational data. Yes.
And this is a different mechanism of generating conditions, or
Here, different from inflation, yes.
Okay.
Yes, it's connected with strong coupling because then we consider equation of motion for scalar or for tensor perturbation. In our model, we will have a non-trivial coefficient here, which depend on time, and they help you to generate a spectrum. It's easier to understand during another talk, yes. Okay, now short, brief, I don't know how to say, talk about some problems we face. Then we use dimensional analysis of strong coupling problem in our models. How we understand that there can be a problem. Valery Antonovich find some interesting paper by Nandi. It's a surname of author. This author considers contraction universe which conformally related to inflation. What does it mean? It means that if something related to inflation, to Einstein frame, it means that in usual simple inflation, there is no strong coupling energy scale at all, only Planck mass, and it's big and everything is okay. All classical scales smaller than it and no problem. We decided to consider in Jordan frame contraction and find out using dimensional analysis strong coupling scale. We find it and we understand that something is not okay because in Einstein frame, in conformally related to inflation contraction, this is not the case. It can be okay. Let us consider the following action for simple action for contraction universe. Here we have some again functions. It's more simple than what we studied earlier. Here we have G2 in simple form and some simple coefficient near scalar, rich scalar. Using conformal transformation, we can go to Einstein frame and obtain a simple module of inflation, well known. Here in Einstein...
I have the following question. Suppose you switch off gravity, yes? What will be the form of the Lagrangian? In this case, the Lagrangian will contain only scalar.
Yes. Here.
What will be... can you demonstrate explicitly the form of the Lagrangian?
In this model, if you, I guess you would like to omit this term, right?
No, suppose I consider flat space-time, yes?
Okay.
In this case, the Lagrangian will contain only scalar field, yes?
Yes.
What will be the form of the Lagrangian for such situation?
Well, here you have some potential term like that, and Planck mass. And
No, Planck mass, I switch off gravity.
Okay, then just action for massive field at
So it will be simply free-form model, for instance,
yes,
and nothing else.
Yes. At flat space, yes.
So your statement that the Horndeski theory for the case of the absence of gravity is simply a free-form model, or I don't know.
I guess Horndeski for sure include this model. For example, if you turn to this Lagrangian, for example, one moment. Here, yes, if you omit this one and this one, here for sure you have any model of phi, phi4, phi3, what you want. It depends on the form of G2.
So you obtain standard model. I mean the kinetic term, which depends on
speed.
plus some potential.
Yes, yes.
Without, and it could be massive or massive.
Massless for sure. And everything, G2 includes these parts, yes. Kinetic term of field phi, its modifications, it can be in strange form here, or standard form of kinetic term, yes, and potential of phi. Or is it some problem with it?
No, then I don't understand what the peculiarity of Horndeski theory. It's simply the Lagrangian of gravity plus scalar field.
I mean, sometimes you may have...
For instance, what's the difference between Horndeski and Ran's theory?
It included in Horndeski. It's a subclass of Horndeski. You're right. It's a subclass. Horndeski Lagrangian includes a lot of models. Browns-Dicke, I don't know, Higgs inflation.
So Horndeski is simple.
Generalization.
It's average Lagrangian, which includes gravity plus single scalar field.
Sometimes it can contain even not single scalar field, but a lot of scalar fields. Yes.
So it's gravity plus only scalar fields, not spinor, not vector fields.
Yes, yes. People also study vector derivatives.
It's average Lagrangian, so it means Horndeski theory.
Yes, scalar plus something. Yes, yes. Plus gravity.
Scalar plus gravity plus condition that no more than two derivatives.
Yes, 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 yes. In equations of motion, yes.
In equations.
Okay, here we go. So we talk about inflation in Einstein frame. Let us consider some simple model where inflation potential flattens out at large fields in future. And as I said, here we have the biggest scale, Planck mass, and that's all. Well-known expressions for slow roll parameters we have in this model, and also from equations of motion with this Lagrangian, with this action, we find out the following solutions. Okay, I also would like to say that for simplicity, we consider only this situation in order to somehow analyze the following things we obtain. So with some addition conditions, but many inflation models admit this condition. Okay, in Jordan frame, where we have contraction, one can choose this function which connect Einstein and Jordan frames in the following form. One can choose another one, but we follow Nandi and take this one. Then our metric after this conformal transformation takes this form. Here we have altogether cosmic time in Jordan frame, and here we have scale factor, this one again in Jordan frame. In this frame, Hubble parameter has the following form, and indeed contraction occurs. Hubble parameter has a minus sign. Everything else is positive. Okay, write down perturbed metric in a slightly different form, but actually it's totally the same as we use in the previous parts of my talk. Again, here we have physical perturbation zeta and everything else unphysical. And for simplicity, in this problem, we consider only scalar sector. So again, write down second order action for zeta and find explicit form of this coefficient here. Okay. Now,
Excuse me. But you can see this, it looks very similar to the model of Linde which here comes.
Yes. It's not super novel model of inflation. We consider it for other purposes. We would like to see that.
So it's very similar to your predictions. In fact, coincide with model.
For this model, yes.
But this model contradicts it.
Okay, but we use it just a toy model.
Okay.
Yes, I agree with you. Maybe we should consider another
Consider
model.
this is the standard top hill inflation, right? Top hill, which starts from the top of the hill.
You mean that start from big?
Maybe not top hill yet, from flat.
Yes.
And you want to understand what?
We would like to understand that if we consider something conformally connected with inflation,
Okay.
then in such model we cannot obtain any strong coupling scales, because in inflation we have only blackness. But we obtain some, it's crazy, but we obtain in Jordan frame some strong coupling energy scales, and it's wrong. It can't be the case because we conformally connected with inflation.
Okay, so another question is, for me it's kind of self-contradictory, the statement that inflation, which is fast accelerated expansion, right? And it's the same as in another frame, this is a contraction.
This yes, it's right, but
so what is the
it's controlled by this function.
Yeah, I understand. But what is the difference then between inflation, expansion, and contraction? So if you have contraction solution, you cannot say contraction anymore. In some frame, it will be expansion. No.
If you don't interact with matter, it's the case.
So if you include interaction with matter in some
then
frames,
you set you set contraction, and that's all. But if you don't interact with matter, nothing.
So you can say this is a contraction.
We should put ourselves to some coordinate system with matter, and only then we can say something that it's truly physical coordinate system. Okay. Next, we again proceed totally the same steps and analyze using dimensional analysis of strong coupling in Jordan frame here. Okay, we find in this simple model, we have quite simple coefficient, even more simple than in Genesis in our previous setup. Find them out in this form through inflation potential. Write down classical energy scale. Now the strongest condition corresponds to Hubble parameter, not with its time derivative. Again, turn to canonically normalized scalar field and rewrite new coefficient for canonically normalized zeta, and compare this naive strong coupling energy scale with classical one. For example, for this toy model, for this potential, we find out that if scalar field is huge, we obtain that this is something less than unity. So it's strong coupling because your classical scale bigger than strong coupling. So something wrong with dimensional analysis here, because we remember that we conformally connected with inflation, and it cannot be truth now. So let us consider analysis of amplitudes to understand real energy of strong coupling. Yes, if we don't know something about connection with inflation, with the Einstein frame, we just close this model, and I think it's not so good because we don't understand the physics here. Now we in our simple model we can simply calculate scattering amplitude for this process. We consider vertices with 3 particles. To do scattering, one can calculate.
Excuse me, in Minkowski space, with A equal to 1?
Yes. For simplicity, we, I don't know, in each moment of time, yes, we have A equal 1. Yes. But firstly, let me note that in this model we have a crucial constellation, and that is why we obtain strong coupling in Jordan frame. For example, if we set one of coefficient in cubic or auto action 0, we find out the following expression. But actually, it's proportional to our naive strong coupling energy scale, and it means that again something wrong. And it's right, because we why we omit this term, we cannot do it, but this example shows us that we have some interesting constellations in our model, and we should take each terms in Lagrangian. We did it, consider the most dangerous terms, find out each matrix element in different channels, our final result here, and actually estimation for strong coupling energy scale here is okay, because this one is small, it's big, and now we don't think about strong coupling problem now. It's okay. What's the I don't know how to say, what's the main idea? The main idea that we should use this analysis, write down all matrix element, find out partial wave amplitudes, and so on. Only then, using unitarity bounds, in the case of one scalar field, it is well known from, for example, from this paper. But in model where we have different types of particles, we need to generalize this unitarity bound, and this is the last part of my talk. For sure, we see in the very beginning of my talk that, for example, in Horndeski genesis and bounds, we have tensor modes and scalar modes. That is why we need somehow modify unitarity bounds, which will contain different sound speeds for tensors and for scalars, for example. Again, we will derive unitarity relation for partial waves amplitude of these processes, and we take only contributions for simplicity of two particle intermediate states. Actually, for many models, many particle intermediate states are suppressed by coupling constants. So our formulas are quite good in this sense. And from unitarity relation, we can obtain unitarity bounds, which we use for estimations of strong coupling scale. But here I would like to emphasize that one can use unitarity bounds with different sound speeds, even in, for example, in condensed matter, because here a lot of perturbations with different sound speeds also can propagate. Okay. So, what we consider? We consider simple model of few scalar field. In this form, we have its action. Recall how S matrix connected with T matrix in this form. Here, M is a matrix element, conservation law of momentum and energy. And we denote P, capital P with prime as final states, two final particles, and this one for initial states. Our initial state has the following form. We have two particles with the following momentum. And here our notation psi and beta connects to set of particles in pair. It means that, for example, consider a theory of two scalar fields. It means that beta can be phi 1, phi 1, phi 1, phi 2, and phi 2, phi 2, such states. And the same for momentum. Notation side connects to momentum of these particles. We would like to obtain optical theorem in this case, in the case of this model, or unitarity relations. For that, firstly, let us obtain the following scalar product states. Why we would like to consider it? Because we want to obtain unity operator with intermediate two particle states from this calculation. Okay, in center mass, where we have the following situation, U1 beta and U2 beta means just some speeds of particles, we arrive to the following formula. Here, the most interesting part is that now we have explicitly these sound speeds, and this is the modification of well-known result. Next, we turn to states connected with definite angular momentum, like that. So this is spherical functions, and we can rewrite this one through this one. Again, our modification is here. L and M is just well-known notations for angular momentum and its projection. Here we obtain, after some calculation, desired unity operator, and here sum means that we some intermediate states with two particles, and this coefficient now have the following form. Okay, now we proceed to optical theorem, to expression for partial wave amplitude. Its imaginary part and its tree level. For that, let us consider T matrix element in this form. Again, it's sandwiched in states with definite angular momentum. This expression can be written as follows. And after some calculations, substitute here this one, we arrive to how T matrix connected with truly matrix element. I don't know how to say M matrix just. Here I should say that we integrated by all other angles except this angle gamma, which is the angle between initial particles. Okay, finally we can connect A and T matrix using this formula, and finally using unitarity of S matrix arrive to something like that. Here we have our new coefficient, which contains some speeds of particle in intermediate two particle states. Finally, we arrived for distinguishable particles. I should say it from the very beginning. I'm sorry. For now, we consider distinguishable particles in a pair. We arrived to this quite familiar but modified result. If we proceed totally the same steps for identical particles, we arrive to something another, from something what differs from previous result. And altogether, we have the following one: generalization of optical theorem. Then we have several number of scalar fields with different sound speeds. In matrix form, one can write it down like that. Here, G is a diagonal matrix, and its component as follows. Okay, finally, let me talk briefly about unitarity bound, how we obtained. Actually, for us, easier to work with rescaled amplitudes now. Then we rewrite everything in terms of these scaled amplitudes and obtain well-known expression, no coefficient here. And here we also restore contribution in more general form from intermediate states with many particles, not only two. Okay, again, in matrix form, we have this one. Now, one can turn to Hermitian matrices like that and rewrite rescaled amplitudes in this form. Then this expression, this unitarity relation, will take the following form. Let us consider the following orthonormal bases with two particle state space in which P will be diagonal. We can consider these bases, why not? Then we, after some computations, can arrive to the following constraints on eigenvalues in this basis. After that, turn to our initial unitarity relation, sandwich it between some arbitrary vector but of unit norm, and write down the following expression. Here we know that this value smaller than 1, this norm is unity, and we assume that this is something non-negative. After that, we immediately arrive that all eigenvalues of this product are not greater than unity, and this is the kind of unitarity bound already. But in simple case, then we have only one type of particles, for example, in the scalars. We can arrive to quite familiar result like that, and this result we can use to estimate strong coupling energy scale, because this partial wave amplitude connects with the matrix element. You calculate all needed matrix elements at needed order and obtain right energy scale. Okay, so here we have studied strong coupling problem using naive dimensional analysis in Horndeski Genesis model. We obtained certain range of parameters of Lagrangian.
I didn't understand the conclusion. The conclusion is that inflation in Jordan frame is not strong.
Sorry. This is. I should turn to this part of talk. Yes.
So this is unrelated to this, the next one.
Yes. No. Sorry. It's related in that sense that we need to construct unitarity bound.
Yeah.
To estimate right strong coupling energy scale.
Okay.
Yes. So this is.
So that the estimate was incorrect.
Yes.
Grosjean. Okay. So
No. Grosjean consider only one. For example, scalar field.
Okay.
One, and his estimation is okay. But if we consider a model with tensor mode and with scalar mode, we need something new, some generalization of unitarity bound.
Yeah, but there was a kind of contradiction. I don't know that in Jordan frame the model is strongly coupled. Right?
Yes. But
this is the conclusion.
No. In Jordan frame, then you consider all matrix elements, take in account all needed terms from Lagrangian. You arrive to the result that there is no strong coupling in Jordan frame.
Because of constellation.
Yes, because of crucial constellation.
Okay.
Yes. And after that, here we consider only scalar modes. So Grosjean results, it's okay. But if we want to study spectrum, for example, another problem involves here we have tensor and scalar, so we need some modification of this result.
Okay.
And this is the last part here, dedicated to this this result. Here we are, and corresponding bounds. And this is super final conclusion of all work. The first part of my talk dedicated to naive strong coupling analysis in Genesis. We find out using this not so right formalism a certain ratio of Lagrangian parameters where classical description is legitimate and model stable and non-singular.
But it is right in the sense that if dimensional analysis tells us it's okay, then it's okay.
Yes, yes. So I guess in this model it's okay, or if you use amplitude analysis, you obtain not so strong condition. My second part of talk connected with trials and errors during construction of various non-singular models of early universe, which we assume with inflation inclination. Again, stability and singularities are explicit, and in the past we don't have strong coupling. And finally, we note that one should use diagrams and amplitudes to analyze strong coupling problem actually. And we, for our purposes, for Valence and Genesis, where we have two different physical perturbations, we modify unitarity relations and unitarity bound. But I emphasize that I guess that these modified unitarity relations and bounds can be used somewhere else in condensed matter and so forth. Okay, thank you very much for your attention.
Questions? There's a lot of you can talk, but maybe.
I have a question. You have a scenario without inflation. So there was an old and sick science about the quantum cosmology stuff. It was describing that the universe kind of was created with quantum fluctuations, and studying the universe, you can understand quantum effects. All of this ended up with inflation, because if there is inflation, you have no knowledge about the initial stuff, and this means that this science is not physics. Yeah, so you can investigate quantum creation of inflationary universe with no results and predictions. So the question is, maybe you can consider quantum cosmology creating kind of universe like this, and then studying, kind of predicting something from kind of quantum effects, which should be seen.
If not mistaken, it's also Mukhanov works.
Okay.
Yes, I mean, maybe I just.
So Mukhanov had this idea, right? When he proposed clination.
Yes, I guess yes.
More questions? Maybe from people in the most. Is that here?
They hear this.
Okay. If there are no more questions, let's thank the speaker again. Да, значит, будут какие-то возражения после положительного заключения? Ну, вроде возражения нет.
Диссертация готова?
Да. Ну да.
Тогда надо было положение защиты, или вот это и есть?
Ну, вообще у меня сейчас, я вот почти доделала бумажку, которую мне надо для выпуска из МГУ.
Формальности.
Я имею в виду на экране показать.
Положение на защиты.
На первом экране публикации, да?
Да.
Положение на защиты, наверное, ребят. Это по-английскому заключение.
Вопросы к публикациям, они могут подойти в
Не, у них вопрос формальный. Положение на защиты.
Ну, они вот просто вот в таком...
бумажке оформляют, он это вопрос.
Ну, придется нам оформлять. Мы все раздельно напишем бумажку.
Нет, в смысле, все согласны, поддержать положение, которое мне нужно. Да.
Ты хотел протестировать? Попробовать. Давай. Какой-то вот... Это проблема, потому что у меня здесь только один вход USB. Это означает, что нужен еще один девайс. Вот это щелкнул, как переключатель. Да. У меня, конечно, есть. Не надо. У меня, конечно, есть этот самый переключатель от Type.
Второй вопрос, это вот то время, которое там, ну, формально надо. Включай вопрос. 5 минут вопросов.
Можно еще у вас спросить? Вот для МГУ нужно вот такая, а те, кто знает, вот нужно такую штуку заполнить, и кого здесь писать? Не важно, у Сергея Владимировича.
Нет, Сергей
хорошо.
уже участвовал. Да.
Да, хорошо. Да. Красненького.
Влада.
Да. Ну, короче говоря, можно сюда всех снять.
Всех присутствовали, все те, кто еще...
Я еще МГУ спрошу, наверное, без разницы.
Может быть, у Сергея есть список просто.
Меня не пиши, а то получится, мы друг другу положить.
Да, просто на следующей неделе выступает.
У меня такая процедура, я на следующей неделе.
И никто даже... Да. Пишите просто кандидатов.
Ну ладно, тогда я тут просто запомню.
5 минут на вопрос, и все остальное я как бы...
Ну да, 25 минут доклад, 5 минут вопросы.
Так, ладно, тогда что писать?
Всем спасибо. Или ты проверить хочешь? Давай.
Приходите на морские чтения всех, кто знает.
Непонятно,
Всех, кто знает. В среду в 11.
В 11, да? Угу.
Тут больше проблем с шумами, конечно.
Где больше проблем? Вот тут вот? Или вот тут?
Звук как из бочки все время.
Вот здесь, да? Из ноутбука?
Яндекс Телемост.
Ну, это может быть, потому что шумит ноутбук. Кто его знает.
Если бы Яндекс мог вычитать звук,
А Zoom гораздо лучше, да?
Zoom также шумел, по-моему.
я думаю, это связано с тем, что это помещение. Непонятно, как с этим справиться.
Сергей Владимирович, вы здесь? Здравствуйте. Так, наверное, непонятно будет.
Нет, вот Сережа.
Я вижу, да. Просто так неудобно спрашивать, наверное, кто у нас секретарь кафедры в МГУ. Я просто вас написала, но вы, наверное, в МГУ не секретарь кафедры.
Иногда я там тоже бываю,
Да?
как человек, который подписывает документы, но, может быть, Сережа что-то еще придумал.
Сергей Вадимович, здравствуйте. Слышно меня? Наверное, в письме это спешу. Ладно, все тогда. Письмо спешу. Это до 20 числа, до 25-го. Ой, ладно.
Алло.
Да. А Сергей Вадимович, здравствуйте еще раз. А вот я хотела... Это вас Юлия Агеева спрашивает.
Да.
Я у вас хотела спросить. Да. Кого нам писать секретарем кафедры для бумаг в МГУ?
Ну, раньше всегда писали меня. По каким-то странным причинам. Мне все равно. Если это важно или не важно, в общем...
Ну, пиши тебя, какая разница.
Хорошо, все, тогда оставляю.
В общем, просто я не знаю, если это какая-то формальная
Ну,
фигура...
там ученый секретарь, или это Майя Павловна дала?
Секретарь кафедры написано.
Может быть, можно Майя Павловна, да, чтобы она была как бы секретарем уж. Там вроде не ученый секретарь, просто секретарь. По крайней мере, вот я вижу файл, который Юлия демонстрирует.
Это официальный образец.
Там написано просто секретарь.
Я не знаю, надо делать, как раньше делали, я думаю.
А раньше мы, по-моему... вот Вика говорит, что Майя Павловна.
Ну все тогда.
Ладно. Ну тогда, наверное... я могу здесь писать рекомендацию без изменений? Это касательно диссертации в ДНКР у нас. Тут было рекомендация без изменений, с доработками.
Наверное, я думаю, что можно написать рекомендацию без изменений.
Ладно, ну тогда вроде все спасибо. Тогда Майя Павловна тут пишу, ее телефон у меня есть, мне надо ее подписать. Ну ладно, все тогда. Спасибо.
Еще такой вопрос. Нам для МГУ, вот мне тоже нужна вот это заключение кафедры. Смотрите, для МГУ нужно делать доклад, или доклад нужно делать для диссертации, совсем диссертации.
У вас аспирантура заканчивается в этом году?
Да, аспирантура заканчивается в октябре.
В октябре заканчивается аспирантура. Когда вам нужно заключение для МГУ?
Для МГУ заключение нужно до конца месяца.
До конца месяца.